So I'm here at the European Space Operations Center in Darmstadt on a press day where it's been very exciting for the Euclid mission. They released 5 images, and I'm with the project manager, I believe, of Thales Alenia Space, Paolo Musi. Is that correct, Paolo? Did I get your title correct? Project manager?
Yes, correct.
Okay.
I am the project manager for industry on
For
Euclid
industry.
satellite.
That's right.
And I'm belong to Thales Alenia Space, which is the prime contractor for the development of the satellite.
So let's talk a little bit about how this project came about. You've been working on you did everything but the telescope, I believe. You did the spacecraft, prime contractor for the spacecraft, and it took 10 years to develop this mission, correct?
Correctly. Right? We started development of this mission in July 2013, and the development included the spacecraft itself, but also the telescope and the science instrument, 2 science instruments, a visible camera and a near-infrared spectrometer. And as prime contractor, we were responsible of everything except the 2 instruments, which were provided by the Euclid consortium, built up by scientists and in overall Europe.
Okay, and so a lot of people probably don't appreciate the fact that industry plays such a vital role in the development of science missions. We know that space industry plays a vital role in Earth observing satellites, commercial satellites, even the defense side of things. But what people don't appreciate is how vital a role industry itself, space industry partners like yourself, play in the development of science missions for NASA and ESA. And so can you talk a little bit about how this works? ESA comes to you and they say, we have this mission. Do you take bids, or do they approach you? How is it actually fulfilled?
First, I would like to spend a few words on the science mission. I think for industry, it's valid in Europe, but I imagine also in the States, a scientific mission do not represent a big volume of space business. Like telecommunication or Earth observation, these are much bigger in terms of volume, but science is extremely important for 2 reasons in my view. One is because it's really developing the edge of the technology, which has then a fallout on the normal business. And the second, because it's quite inspiring for young people. I think it helps a lot to get together the best energy from university, the best resources, and work on space project. Now, on how the ESA is organized to develop science missions. They usually do a feasibility study, 2-3 study in parallel with different industries. Then they for a couple of years, and then after a mission is proved to be feasible by the feasibility study, then they make a competition. And in the competition in Europe, they select the prime. And then when the prime is selected, they award a contract to the prime, and then where the industrial story starts.
So what was the most difficult technical aspect of this particular Euclid mission?
I think if we start from the telescope, this telescope is unique in its kind because it merged 2 characteristics which normally they go in exactly different direction. One is the very high accuracy, which normally drive a small field of view, while here in Euclid we want a large field of view, half a degree, because the mission of Euclid is to make a sky survey, and larger field of view means a shorter time for the survey. So the telescope itself combines these 2 characteristics, normally diverging. And then, since we have an accurate telescope, very accurate telescope, we need a very accurate stability of the pointing system, because don't want that the image move during 10 minutes of exposure time of each images. And this we do it with 2, let's say, special design. One is a fine guidance sensor, especially built for Euclid, and the second is a micro propulsion system, which compensate the small motion of the spacecraft with a microthrust of the order of micronewton. So you can imagine a very, very small force which compensate, for example, the drift of the satellite due to the solar pressure on the solar wing.
And you had a bit of a problem with the fine guidance sensor with the software, I believe, correct?
Yes, correct. We, during the commissioning phase, we tested the performance of this guidance sensor in a wide range of star density, from the field of view with very few faint stars to the field of view densely populated with stars. And we have seen that at the two extreme, the star tracker was, let's say, a bit confused by the noise generated by the cosmic rays. So we
and cosmic rays, for those who don't know, are just basically charged photons
exactly
that come from the galaxy, they can come from either the sun or the galaxy.
There are two kinds of charged protons. They can come either from the sun or from the galaxy. The two sources are not normally at the same time, but they come from different directions. In this case, they are more from the sun.
Okay, these were from the sun, and they were interfering with the ability of the.
What they really do, they generate a kind of fake stars on the sensor, and these fake stars in a normal star field, the FGS could manage them, but in the star field with very few faint stars or a lot of stars, they were confusing the algorithm. So we decided to implement an extra piece of software which could better manage this spurious star and get rid of them. We gave a bit more time to the FGS, to the fine guidance sensor, to capture the image, to increase the signal to noise ratio, and also we developed an algorithm to really discard the fake stars. And this was done in a intense period during summer. It was then uploaded on the spacecraft mid-September, and then since 6 weeks now, is behaving quite well in space.
And so the hope is, to put a fine point on it, by January of this coming January, Euclid will be doing routine science observations at the start of its 6-year science mission. Is that correct?
Exactly. From January, the real survey will start. They will start a nominal science operation, which means a systematic survey of 35% of the sky with the onboard timeline, which scan the sky step by step continuously. Why 35% of the sky and not 100%? Because the rest of the sky is somehow hidden behind our galaxy. It's not so nicely visible from Earth. There is the Milky Way in front of it, and we cannot penetrate and go deep in the sky through our galaxy.
And one final question, that is, it's a 6-year nominal mission, which means it's going to run for 6 years unless there are any major problems. But the hope is that you're going to be able to double, that ESA will extend the mission, and you yourself would probably know better than anyone, does it have enough fuel to last 12 years in space?
Yeah, of course, there are predictable things and unpredictable things. As far as we can predict now, based on the consumption that we have seen on board in these 3 months, we can project that the expected lifetime is much more than 6 years. It could be as long as 11 years.
11 years?
11 years.
Great.
And this is driven by the availability of nitrogen, of the coal gas, which is used to really compensate for the small, let's say, disturbances on the spacecraft. Of course, there could be unexpected things like failure or so, and then this extra budget of fuel could be quite useful also in case of, let's say, emergency. But the nominal fuel consumption is much better than predicted.
Well, thank you so much, Paolo. Thanks for taking the time. Congratulations on a job well done, and we look forward to hearing more about the data that Euclid and your team has enabled. Thank you so much.
Thank you. Today is a very nice day for Euclid, I think.
Thank you.
Thanks.